Alright, welcome to another AQA chemistry video. Today I'm going to be doing a video on group 2. So now we finished about the topic of the periodic table. As simple, inorganic chemistry goes really quick. There's very short topics. And now this is the only topic about group 2. So now I'm going to be going into group 2 in a bit more depth. So still on inorganic chemistry. There's like what? I say after this will be the end of group 2, then there'll be group 7. There's like 3 videos on group 7, and then the rest are exam questions, and then that's it. We're done with inorganic chemistry. So yeah, I'm gonna get straight into it. So properties of group 2 metals. Elements in the same group have similar properties. Here we're gonna take a look at the similarities between the properties of group 2 elements. So I've kind of already gone through this in the previous video, but here I'm going to be just going over it again in a bit more depth. But if you want to watch my previous video again about it was just talking about the different traits that group 2 metals have, different periods have. The last one's more about periods. These ones talk a bit more about groups, but I'll focus. This one is just specifically about group 2. But I did in the previous video talk about the ionization energies, the melting points, size, and so on. And this kind of goes into a bit more depth specifically for group 2, because that's one that they like talking about in the exam quite often. All right, now I'm gonna shut up and actually go through it now. So, atomic radius and ionization energy. Atomic radius increases as you go down group 2, and this is because each extra electron shell is further away. Ionization energy decreases as you go down group 2, and this is because the outer electrons are further away and experiences less attraction to the nucleus, as you would expect, right? So just the more shells there are, because you're going down a group, you're increasing the number of shells. So that valence electron shell is further away, and there's more electron shielding, and there's the distance is also physically further away. Yes, there is an increased nuclear charge, but the fact that there's more shells kind of overall means that there's a lower electrostatic force of attraction between the nucleus and the valence electrons on the outermost shell, on the valence shell. Melting points decrease as you go down group 2, and this is because ion cores have larger radii down the group. The free electrons experience, or the delocalized electrons experience less attraction to the nuclei because of the larger radii. The bonding is weaker, so the melting point is lower. So remember what you need to remember how metallic bonding works. You have your metal ion core, so it will be your it's pretty much a cation, right? You have your cation, and then you have your delocalized electrons that come from the valence shell. Electrons from the valence shell are then lost, right? But then you have to remember that these cations are much larger because they have a larger I say ionic radius, you can call it. Actually, it's ions, you call it an ionic radius, really. And so the nuclear charge is bigger, yes, but the size, as it's the same principle as before. More shells, and so those delocalized electrons have a weaker electrostatic attraction between the positive core nucleus of the cation and the outermost electrons, or those delocalized electrons. So magnesium, as you go down the group, you'd expect to have a lower melting points. So I haven't got my periodic table with me right now, but beryllium, magnesium would have like generally the highest melting points, right? But magnesium is a one anomaly. So magnesium has an anomalously low melting point, so it doesn't follow the trend. And there are, as I said before, there are examples where certain groups, certain atoms, or certain trends have a kink to it. So magnesium has an anomalously low melting point compared to the trend, where you'd expect the melting point to go down, in regular amounts. And that's because it has a different crystal structure to the rest of the group 2 metals. So that's why it has, it's even lower than, I don't know what's the element under magnesium. I should have got my periodic table with me here, but it's even lower than that. But that's just because it's one anomaly, but because of the different the different crystal structure. Reactions with water. So group 2 metals react with water to form metal hydroxides. For example, magnesium plus 2H2O goes for magnesium hydroxide plus H2. And reactivity increases as you go down group 2, and this is because there's a lower because lower elements have a lower ionization energies. So I've already explained to you the ionization energy, the the reasons why it would have a lower ionization energy, or why it would have a weaker electrostatic attraction. Lower ionization energy is because of that weak electrostatic attraction. I'm not going to go into that again because I've already said it enough times now. But as you go down, obviously that ionization energy would decrease because there's a lower electrostatic attraction, right? And that means if there's a lower ionization energy, less energy is needed to obviously to remove that electron, and therefore the rate of reaction is going to be quicker because less energy is needed to remove that electron, right? So therefore the rate of the reaction would increase as you go down the group. And you can see that with the water experiment, beryllium beryllium actually doesn't do that, but magnesium, you can see it's not a very rapid reaction. But as soon as you start going down and down that table, and you start going to the bottom of the table, because the ionization at the very bottom of the group 2 metals, right, they would have the most the ionization energy is so poor, the reaction is nearly so quick, right? And then that type of reaction is so fast, we describe it as being explosive even. So beryllium is an exception. So reactivity increases as you go down group 2, and this is because there's lower elements have lower ionization energies. And beryllium is an exception because if beryllium were to lose 2 electrons, it would be very tiny and have a very high charge density, and this would make it unstable. And so beryllium doesn't actually react with water. Solubility of salts. The solubility of hydroxides increases as you go down group 2. So magnesium hydroxide is very insoluble. The phrase to use for this is sparingly soluble. And the solubility of sulfates and carbonates decreases as you go down group 2. So barium sulfate is completely insoluble. So I'm going to go through this, right? So if you're talking about group 2 hydroxides, and then group 2 sulfates, SO4 2 minus and CO3 2 minus. Generally, right? So for solubility increase, let me just double check, make sure I don't say something that's completely incorrect again. Yes, yeah, as expected, yeah. So solubility increases as you go down group 2 when you're talking about hydroxide. So metal hydroxide, so group 2 metal hydroxide increase with solubility as you go down the group 2, whereas group 2 sulfates or carbonates increase in solubility as you go up the group, right? So the 2 minus, remember this is a 2 plus charge, right? 2 plus, group 2 has when they form ion state, they're in 2 plus charge, right? I'm not gonna. This is the one thing that I can see why, because it's 2 minus here, 2 minus here. Whenever you're talking about an ion that has a with a 2 minus, right? You just know that it's related to its solubility would increase as you go up the group. You don't need to necessarily know why. Probably do, but I've never really encountered a question where they ask you specifically why. But if I had to really work out, I could probably something to do with that, right? But all you need to know is that you don't have to worry about that, about explaining why. But all you need to understand and just know is that solubility of hydroxide, so 1 minus charges generally, they increase as you go down the group. But solubility of SO4 2 minuses or just 2 minus charged ions would increase, or I should say ion. It'll be a compound, right? It'll be hydroxides or sulfates or carbonates, metal sulfates, metal carbonates. So metal sulfates and metal carbonates would increase in solubility as you go up the group, and that's it. And we have uses of group 2 compounds, right? So you need to understand. So those are things that you need to understand about in questions. So like the reasons why this is important is because they link into this, right? And then the uses of group 2 compounds. You actually need to know some of these examples for your exam. You actually is required for you to know some of these. So group 2 compounds have a number of uses in industry and in society. Example of these include wet scrubbing. So wet scrubbing is a process of removing SO2 from flue gases. Flue gases come from chimneys and industrial waste, so they form industrial waste. calcium oxide and calcium carbonate are used to remove SO2 from the gases, and this is because they work because SO2 is an acidic gas, and calcium compounds are generally basic, so it's a neutralization reaction, right? So the calcium oxide is mixed with water and sprayed onto the gas. It's usually the SO2 gas will be funneled through a chamber, and then this calcium oxide is mixed with some water, and it's precipitated. It'd be kind of like I've got a shower head here, right? And it'll be this gas that's getting funneled. It'll be in a massive chamber, right? Massive, massive chamber. Right, well that hasn't really worked out the way I wanted it to. But you get the general point, right? This SO2 gas gets funneled through from a chamber, so funneled through by a pipe and into this chamber, right? And there's this there'll be a store of calcium oxide that's been dissolved in water, and that will be precipitated onto the SO2 gas that's now in this chamber. And what it does now is you're kind of neutralizing the acidic gas, and the calcium oxide and the byproduct that you're forming is called calcium sulfite, which is CaSO3, and that neutralizes it. That's all it is, and yeah. Alright, so there's other uses. So that's the one thing that you can use for. One use for, like, for example, for calcium oxide, and then in healthcare, this is one that usually comes up most. I say usually comes up. The one that is easiest to remember that for people. So, one of them is barium meals. So as I said before, solubility increases as you're going up group 2 when it comes to sulfates or carbonates. So down the group, is it? Wait, let me double check again. Yes. So very far down the group is yeah, I was right. So is barium, or down group 2. I should have got my period. I really should have got my periodic table. But barium sulfate is really down group 2. So barium sulfate would be very insoluble because it's like near the bottom. Therefore, it's very good in healthcare. So barium meals, which is made up of barium sulfate, are used in healthcare, and that's because barium sulfate in itself, because it's insoluble, it means that it just passes through. What they do in healthcare when you're having surgery or need to take an X-ray scan before you get surgery or whatever, or if they just need to get an X-ray just in general, they'll make you eat a barium meal because barium is actually very good at absorbing X-rays, because X-rays are very good at detecting solid materials like bones, but not very good at detecting soft tissue. So if you didn't have a barium meal, and they just took an X-ray of you, and if they wanted to examine your intestines, your esophagus, or anything like that, it would be very difficult to see under an X-ray without taking a barium meal. And what barium meal does, I should have probably got a picture of it actually. You know what? I should have got a picture. Alright, so I finally got an image of it. I finally decided to probably just get an image of it. But yeah, so it's as you can clearly see here, right? If I didn't have a barium meal, you can see the bone structures in here, because that's as the X-rays are very good at absorbing, are being absorbed by like hard structures. Yeah, X-rays. So barium meals are insoluble and they reflect X-rays. I say absorb. I say reflect back. Once it hits it, they reflect back. That's what I meant to say, not absorb it. Sorry, before any physicists kind of come at me. But barium meals are insoluble and they reflect back X-rays. And barium meals coat the esophagus, stomach, and the intestines. Anything that's obviously here, they're just talking about the digestive system. So barium meals coat the esophagus, stomach, and intestines, and make the structures of them sharp on the X-ray. And that's what we want. All we want to do is just be able to examine them. So obviously there are, like, obviously the kidneys behind here, the liver. Obviously they don't get easily seen because obviously they're not part of the digestive system necessarily in terms of the fact that the barium doesn't pass through it, so you can't really see it. But obviously we can still see the stomach here. We can see the intestines, and this is what they'll use it for, right? And this is what they'll kind of see. I haven't got the right word for it. It's a contraction of sorts. There we go. It allows them to say, okay, look, all of a sudden, right? They can say in their head they're thinking, I'm not really a doctor, so I can't really give you the best idea of it, but from what I can see here, if I was asked, it's going from the stomach, going towards the duodenum, and it's this massive contraction here, this massive, and it's preventing the passage of this barium here, because it's not as illuminated as before, and that tells me there's some sort of blockage here, and it's because of that, because the reason why it's not here is because there's not as much barium sulfate around here, and that's what's causing it to and that's why it's a more faint image, and that allows doctors to say the reason why the reason why a patient isn't absorbing as much food as they usually do is because there's this contraction here. So that's why these barium meal is helpful, because they can make an assumption, they can make a diagnosis based off this information, because they can clearly see from the X-ray the barium isn't able to pass through here, and that may explain to a patient why they may not be able to absorb their food properly, because it's not being able to pass because this blockage here. Look how white this is, and look how not that very white this is, right? So that's why they're useful. So obviously you don't need to know in all of that in depth, but the idea is you to understand why barium meals are useful in the industry. And this is all you need to know for your exam, is that they're used in healthcare to kind of, as they're used for barium meals. So in healthcare, barium meals are used, or barium sulfate, because it's insoluble, and they can use to line the digestive system when using X-rays, because they reflect X-rays, and they can use for X-rays for scanning. And that's all you need to say. You don't have to go in depth and analyze this, but for you to understand what's actually going on here, why it's useful, I kind of thought this diagram might be helpful for someone. If that's wrong, by the way, don't quote me. I'm not a doctor, but that's what it looks like for me from what I can see here. All right, so they also group 2. One of the uses of them is that they can act as bases. So this is another example you need to know. One of them was this one. Obviously, the other one was wet scrubbing, but yeah, in healthcare, in industry, and they also act as bases. So agriculture, right? Farmers use calcium hydroxide, sometimes it's called slaked lime, and magnesium hydroxide, because they would be yes, is it? No, they're not soluble. They're not soluble. Yes, calcium, magnesium hydroxide aren't soluble, but calcium hydroxide is used to neutralize acidic soil in agriculture. So farmers will spray this onto the soil to neutralize any acidic conditions that are in the soil. You want neutral conditions for your crops to grow. Maybe some plants will need a more acidic or more alkaline condition, but for most crops generally they need a neutral condition to grow. Maybe slightly alkaline, I think. So calcium hydroxide in particular is used to neutralize acidic conditions and acidic soil in agriculture, and magnesium hydroxide is actually used more for humans, and it's usually given as a magnesium milk. You might see like a little tablet when you go to your pharmacist, right? Or like a little. Sometimes they even have examples on adverts. All it is magnesium hydroxide, and it's used for indigestion. And this is usually because of acidic conditions in the stomach that may have passed down into the intestine, and that all this is magnesium hydroxide. Remember, it's basic. Magnesium hydroxide is very, very basic. It's dibasic. Because of that, obviously it's not the most basic. There's other things that are more basic than that, but the idea is that magnesium hydroxide is basic, and it's used in indigestion tablets as an antacid that neutralizes excess stomach acid that may have passed down to the duodenum or down the intestinal tract, and it just solves indigestion. So, but as I said before, you don't have to go into ultimate depth. Just say calcium hydroxide used to neutralize acidic conditions in soil, and magnesium hydroxide can be used as indigestion tablets. Usually it's given as a solution from what I've seen before, but indigestion tablets, that's the one. So say indigestion tablets. And then the last one is titanic extraction. Now this is one I don't see as much, so be wary of it. I don't really see it that much, but in case it comes up, or just knowing it, the first step in the extraction process is converting titanium ore to titanium chloride. it's smelting really, right? So converting titanium ore to titanium chloride using chlorine gas and carbon, and in the second, so once you've converted this using chlorine gas and carbon and then you smelt it, the second step involves heating TiCl4 with magnesium metal at 1,000 degrees Celsius. An equation is given here, right? You don't need to. For me personally, I have never really seen this in the exam, which could mean that it will come up because they like bringing things that that normal people bring up. But talk to your teacher about this. Me personally, I say talk to your teacher about this because I never I have studied this. It is in the curriculum, but I've never really seen many examples of it. But just knowing that though in fact no, I've seen a question on it, but it give you enough information for you to answer the question. You don't need to know the 1,000 degree part, but just know that the TiCl4, the titanium ore, can be converted to TiCl4 using chlorine gas and carbon, and then from there just simple. They tell you that you're getting titanium from TiCl4 and magnesium, right? So you just balance your equation. You know it's going to be, you're forming Ti, you have TiCl4, you have magnesium. You're going to form magnesium chloride, and it's pretty simple from there. So anyway, hopefully this video was helpful, and hopefully I didn't talk too much.